Hello everyone, we are from section 2 group 1. So today we are going to demonstrate some optimizations that can be used to improve the performance of our Gaussian filter. So first of all, let us recall back the original code. So this is our original code, which is a Gaussian filter. We have a kernel with 3 times 3 size, which is 121, 242, and 121 divided by 16. So we initialize a local buffer, which it will load the image into the local buffer, and then they will perform multiplication between the kernel and the local buffer, and then here is the filtered image. So the filter image used is the LAN9512 in the part 2, which is the project 2. So we introduce 3 methods to improve the performance. The first one will be the buffer is removed from the original code. So you can see the kernel is still here, but the buffer is missing. So we directly multiply the kernel and the images. So we will get the filter image through these direct multiplications. So the second method is we introduce the unrolling factor, so which we have unrolling factor of 6. So the factor of 6 means it will perform 6 different elements at the same time. So for example, we have local buffer J0, J1 until J6. So it will load the image from, for example, I0 until I6. So it will perform six multiplication at the 1 clock cycle. So the next one is, you can see here's the HOS unroll, which it performs the complete unrolling. So from -1 to 1, so it will perform 3, 3 for loop. For here, we can see it will perform 3 summation, which is the sum here. So 3 at the 1 clock cycle. So the next one is data flow. So for the data flow, it will allows the read image and apply kernel to run concurrently, which means that you can see there's a local buffer here. So we will perform the read image process. So until we load the things into the local buffer, we load the image into the local buffer. So the apply kernel will immediately process the local buffer, the image, and then get the filter image. So without waiting the read image to finish executions. So this is a very important process. So as you can see, since we don't need to wait until the read image to fully execute the code, so we can definitely save the time and also energy. So the next one will be pipelining. So the pipelining, you can see here is the initial interval of 5, means 5 clock cycle. So whatever after 5 clock cycle, even though this code is not yet finished, so it will perform another one from J until 0, then it will perform the J is equals to 1. So it will finish immediately after the first clock cycle, first 5 clock cycle. So the next one is still same as the previous code, which is the unrolling. So back to our slides for today. So here's the output of no buffer. So you can see, the resource definitely is smaller since we no longer having a buffer. So the memory use will be reduced. So this will be the buffer, unroll, and data flow, which we have performed the unroll and data flow. So the data flow which means the read image and the filter image will perform concurrently. Yes, the result so definitely contributes to the latency and also the total power and also the negative slacks. So here is the unroll and pipelining. So same goes to latency and also the powerful because they can perform, reset the pipelining after 5 clock cycle. So we will compare the data flow and the pipelining, which one have better performance in terms of latency and which one have the better efficiency. So here's the result. So baseline is our original code. So definitely the without buffer one use the least resource compared to others because it no longer have a buffer. It uses less resource to finish the process, the whole process. And in terms of latency, the data flow, since they're running concurrently, so they have a lowest latency. So you can see from here. And then using the pipelining, we can achieve better energy efficiency. So these two are the pros and cons. As you can see, if you have, although this one have a better latency, but doesn't mean that it have a low energy because you need to recall back for the total power. As you can see, here is the total power for the data flow, which is 0.4 plus 0.3. And then this for pipelining is 0.4 plus only around 0.2. So here's the strength of the pipelining methods. So here's the conclusions. So removing buffer can definitely reduce the total resource use. So implementing the pipelining optimization can have a better energy efficiency, and implement the data flow can reduce the latency. So thank you very much.